Participants. What? It's the wrong meeting. There we go. All right. Oh, I know. I forgot. Hey, let's get started, I guess. It is 9:01. I mean, 11:01, sorry. We are broadcasting today from an undisclosed location in Sonoma County, being as headquarters is currently under an evacuation warning from the fires. So I just came down to stay at my brother's for a while. A little easier to sleep at night. And the disadvantage, of course, is I don't have my whiteboard. So we'll have to sort of fake that. Door is slightly open. Yeah, so first of all, are there, oh wait, I'm not keeping up with the chat, hold on. What is going on? Okay, yeah. Yeah, so first question, are there any questions or issues you want to bring up? Yeah, Nick, it's possible that I got your email last week. there isn't any other email I prefer. It's just that last week was so completely crazy. There were probably a lot of emails I didn't read. So let's see. What I think I would like to start with is just sort of a recap of where we left off, because there was a lot of information there all at once, and I think we can kind of slim it down a little bit. So here is where I would first look, and I guess in order for this to make sense, I have to share my screen. Hold on. There's my meeting. Share screen. Okay. Yeah. So remember that there is a topics page. It's linked. Option. Can everybody see that red circle, by the way, when I draw it on the screen like that? Why won't my... This is crazy. Why can't... Whoops. Didn't need to do that. All right, now it won't let me bring up the chat window. Up there it goes. All right. So anyway, the topics page is where I will try every day that we have class within 24 hours is my goal, to just post a summary of everything we did in class. And this is the closest I've ever gotten in this course to having actual notes for what I cover. And then most importantly, on the right, there are links to the code examples that we've discussed. And the most important one in this case is example 1A, which really is the most concise rendition of the fundamental steps, which I'm putting at the top of the browser there. Namely, what do we have to do hello world and get something on the screen in WebGL? So there's really two major parts. First of all, there's just the initial setup, where you get a graphics context from the browser. You load and compile your shaders. You can have lots of them if you want, but you need at least one vertex shader and at least one fragment shader, no matter what. In the shaders, you're going to define what are called attribute variables. And really, in order to do anything, you have to have a vertex attribute representing its position. Later, we're going to see that you'll have lots and lots of vertex attributes. But let's just, I'm going to collect some. What if I just take a blank text window and give you a big font? And why isn't that getting bigger? Is that better? Not really. Okay, why won't my text font get bigger today? Plus, no. Well, see if you can read this. So the purpose of an attribute variable in vertex shader is for us to pass per vertex data from the CPU to GPU memory. That's basically the purpose of a vertex attribute. And we are starting, if you remember, I'll bring up the vertex shader code. Okay, so here at the top, this is our vertex shader. Very, very simple C-like program. But the important piece is this declaration of a 4-element vector as an attribute type. And what that says is that, okay, we are going to have to supply data for this attribute. And that data is going to be different for each vertex, or at least it can be different for each vertex. So we have to supply enough data so that each time the vertex shader runs, it can grab a new block of values to fill in that vec4. And in our case, we want 6 vertices. So when we supply the raw data, we have to have, in this case, 6 pairs of numbers representing 6 positions. And I think we mentioned last time that even though it's a 4-element vector that's representing the attribute in that shader, we're only supplying 2 values. And that's okay, because it'll fill in the other 2 coordinates with defaults that are appropriate. And we'll worry about what those are later. So now remember, these are just coordinates of a triangle, and these are coordinates of a second triangle. And we're thinking of these as X and Y, and we're ignoring the Z coordinate, right? So that's kind of where we're at to start with. So going back to the steps, we have to get that data over to the GPU, and that's done by just putting it in a chunk of GPU memory called a buffer. So we create a buffer, which gives us a handle into GPU memory, and then we have to fill it with data. And if we look at the code for that, maybe you'll remember this when we go to our entry point here. This is what the steps look like. And what I've done in this example, this is GL example 1A as opposed to GL example 1, is I've taken all the boilerplate code and I've moved it into a utility file because it will never change from this day forward. So there's no point really even looking at it. So this helper function create program, good question, hold on a sec, is what actually goes through the steps of grabbing the source code out of the HTML file, sending it to the GPU, telling the GPU to compile it, and if it compiles successfully, it will create what's called the shader program and return it to us. So this is again, just a handle representing a compiled vertex and fragment shader pair called the shader program. And no, you can't overflow the buffer unless you run out of memory. It's dynamically sized based on the data that we pass. So in this case, vertices, remember, is just a JavaScript variable representing a typed array full of data. And it's the process of passing that data via this create and load buffer function that is going to essentially size the buffer on the GPU. And it's maybe worth taking a quick look at that. I stuck this code in a file called cs336util, and if a second, which one did I want? Create and load buffer. I mean, you might recognize these steps. This is not too complicated from last time. Right? We call create buffer to allocate. Well, we're not even doing the allocation at this point, honestly. What we're doing is we're essentially getting a handle to memory that will be allocated when we pass it data. And then in order to talk about it, we have to bind it. So the buffer is now associated with this register called array buffer. And then we say buffer data, we refer to the register and we pass in the data. And the third argument, static draw, don't worry about that. It is not, it's a hint about how to allocate the memory, but we don't care. And then once we've filled the buffer with data, we can unbind it from that binding point. Okay, now why did I bring this up? I want to show you something because this is really useful and you should look at it, which is, where did it go? So this is an excerpt from this book, WebGL Programming Guide, the one I call the Teal book. And I just pulled it up this morning from the ISU library. Just go into the ISU library, make sure you're on the VPN if you're off campus, and search for WebGL Programming Guide and click Online Access. And Bob's your uncle. Now, the reason I like this book is because it explains things very slowly and carefully with lots of pictures. Um, the thing I don't like about this book is that it doesn't have page numbers and it doesn't have section numbers. So I can't tell you, look in section 3.15 and you will find this example. But the picture I'm looking for is this one, which is in chapter 3. They're doing this example by drawing 3 points. And I decided to just start by drawing triangles because that's what we're going to do the whole semester. But the picture looks like this. You've got your JavaScript program, and the shaded stuff, the way you think about the shaded stuff is that that's what's on the GPU, and the stuff that is outside the shaded box is outside the GPU. So you've got your vertex shader on the GPU, and you've got this attribute variable, which you can kind of think of as spanning the boundary between the CPU and the GPU. So what happens then is that you notice he's shown these two register-like things, which are as little boxes. And one of them is called array_buffer. There's another one called element array buffer that we'll look at, I think, later in the hour. And so the first thing that happens is your call to GL create buffer. Whoops, what did I just do? Let me try this. The call to right here, GL create buffer, gives you sort of an amorphous kind of buffer object, and you get a handle to it. Oops, and I have to do this to be able to scroll again. Let's scroll again. When you call GL bind buffer, what that does is it associates that chunk of memory with that register, the binding point GL array buffer. There's no rhyme or reason to this, honestly. It's kind of a stupid design as far as I'm concerned, but it's just the way the API works. That in order to call a function that manipulates or talks about a buffer, you have to have the buffer bound to an appropriate binding point. Okay. Then the call GL buffer data is right here, actually transfers values from your JavaScript program into that buffer object. And I think that's as far as the initialization part goes. We'll come back to this book picture in a sec. Typically, in a typical example, you'll have lots of buffers full of data because you'll have multiple vertex attributes. You'll have multiple objects, each with multiple vertex attributes. So there could be a lot of data that you have to pass, right? And this, we're just doing a hello world that's as simple as it could possibly be, believe it or not. Okay, the remaining steps that I've got listed here, in our first example, we only did them once, but the reality is these are typically going to happen every frame. So typically 30 to 60 times a second, because again, our applications are likely to be dynamic, right? They're going to be animated, they're going to move, they're going to respond to input in some way. So we're not just going to draw once, we're going to draw once every frame. So what do we have to do then to draw? Well, we have to bind the shader. So in each call to draw, we can only use one shader object. But each frame, we could bind a shader, then draw something, bind a different shader, then draw something. So this could happen many times. But then we iterate over the attributes. And the thing that has to happen here, remember, is the purpose of the attribute is that this represents the per vertex data that we provided in that buffer. How do we associate the data with the attribute variable? And, well, we bind the buffer so we can talk about it at all. We set what's called an attribute pointer to the buffer. And this is really just another set of registers, the attribute pointers. Every attribute is given an index within the GPU, and you just associate that index with the handle to that buffer. And then finally, and once again, this is a step I have never been able to think of a reason for this to exist, but it's just the way the API is. You have to enable the attribute as a separate step. So let's look through those in the pictorial sense, where we've now got things initialized and we want to think about drawing. And as you can see in this book, there's a lot of careful explanation of everything. So if you feel like I'm going too quickly, just take a look at this text. And as I mentioned, I found this book pretty helpful when I was trying to make the transition from doing OpenGL and C++ to doing the WebGL version. This was helpful. So now what happens is we have control. It's this called vertex attrib pointer that sets up the relationship between the data in the buffer and the attribute variable. And the way that they've drawn the picture is that you've sort of got a connection of some kind. There's a pointer from here. I don't know why the arrow is drawn going that way, but there's an association that's based on sort of a set of registers from the attribute variable over to the data, but it's not quite there yet. Notice how he's drawn it as an open switch. And it's enabling the attribute that sort of closes that switch and actually gives you the connection between the attribute variable and the buffer. And when we look at that in real code, let's do that. This would be in our draw function. No, I don't want, that's not the code we want. Hold on a sec. Close, other. I want GL example 1A. So when we go to this draw function, we clear the frame buffer, bind the shader. We're going to bind our buffer with the vertex data. And then we have to look up the index that defines that attribute variable. And if we're successful, we'll go on and we need to enable it and we need to set the pointer to the actual data. And so that's based on the index that we selected. And notice that this function call does not mention the buffer. Remember, we're working with this state machine. Whenever you are doing something that involves a buffer, you bind the buffer to a binding point first, and then you call a function that depends on the buffer, and it uses whatever is the currently bound buffer. So that's why the function call doesn't mention the buffer at all. We're relying on the fact that we bound it up here, so that's the buffer that we're talking about. And these next two arguments are actually critical, right? When we set up our buffer, we're providing data for a variable of type vec4, which is a 4-element tuple, and yet we're only providing 2 floating point values for each one of those, relying on the GPU to fill in defaults. And so we have to tell it at some point that, oh, look in that buffer, and for each time you run the next instance of a vertex shader, grab 2 floating point numbers, and that's your vertex data. And that's what we're telling it there. So that's that. And then the last thing that happens, and let me return to this reference. I think this is the right, is this the one I want? Yeah, this is the one I want. So what happens next? Well, the most important thing is that we're going to draw, which is where you specify, well, I've got my data on the GPU. I've got the data associated with a vertex attribute. In this case, it's just the vertex position. But that still isn't enough information for something to be rendered. You have to tell it what to do with those vertices. How are they supposed to be grouped and used? And I can tell you that 99% of the time in this course, we're going to group them as triangles. And that we'll use the default, which is it just takes every 3 consecutive vertices in the buffer and groups those as a triangle. Now, there are a number of options there that I guess we ought to explore, but this is typically what we'll do, is just draw triangles taking groups of 3. Now, if you look at the previous line, it says set uniform variables. And we haven't talked about uniform variables yet, but if you think about it, it sort of makes sense. An attribute is data per vertex. So each vertex can have its own position. But what if you just wanted a global variable that was the same for every instance of the shaders, and it didn't have to be different for every instance the way the positions do? You would use a uniform variable for that, and it's infinitely more efficient to do that, rather than just pass the same value to every vertex shader over and over again. In an example like Hello World here, it's hard to notice the difference really because we've only got 6 vertices, but we'll be rendering models that have thousands and thousands of vertices before long. And then you can see it really is going to make a difference in efficiency if you can do something as a uniform variable, because it's like a global constant. Now, let me see. Somebody said something that was probably an intelligent question. Yeah, that's a good question. Is there any application where you would not use triangles? I'll give you 2 answers. There are cases where it's more efficient to use what's called a triangle strip or a triangle fan, and I'll show you what those are momentarily. The other thing is, for purposes of debugging, you often will end up drawing lines or points, because if you're rendering something and you can't figure out why it isn't rendering correctly, what I'll often do is draw it as lines and make them bright red, so I can better see what's actually happening when I look at the screen. For example, sometimes when you're trying to understand what a model is doing, you'll want to draw it as a wireframe, right? And you sort of get a different view of what's being rendered because you can see all the way through it, and you can see where the boundaries of the polygons are quite a bit better. But we'll come back to uniform variables later. I just wanted to make sure that we sort of got through, where are we? Got through another view of what these steps are. And I'm encouraging you to take this particular example, GL example 1a.js, and read it, I don't know, 30 or 40 times. I mean, you really want to internalize what all these steps are, and reading the code is the best way to get a handle on it. Okay, and so finally, when we draw, remember, you have to specify the primitive type, and you get to specify what portion of the buffer to use. And this just says, I'm going to start at the 0th vertex, and I'm going to draw 3 vertices. So this should draw 1 triangle. And it's easy to debug this. I mean, we can say, all right, if I just go from 0 to 3, and we render this, where's my thingamabobber? GL example 1a HTML. All right, I'm only getting 1 of the triangles. If we go back and uncomment the second one, you can see I'm getting the 2nd triangle, right? So that's another thing to get used to. Let me do an example that is, I don't want to get too far into it, but this is a simple demo of what the other primitive types are. And I call it the list example. And you can try this. There's a little drop-down list. And if you're curious how to do a drop-down in HTML, it's simple, and you can read the code. But basically, what I've got is a buffer with 8 points, and they are indexed. Control. Just a second. I can do this. D, C. No. Anyway, they're indexed starting here, 0, 1, 2, 3, 4, 5, 6, 7. So that's our buffer data. And the question is, what do all these different primitives do? So you can see what points do. That's not too surprising, right? I have to If we do lines, what does it do? And you can see that what it's doing is it's taking the first and second point, rendering a line between them. Then it takes the next 2 points, renders a line. The next 2 points renders a line. The next 2 points renders a line. That's what that does. Other variations are line strip, where it groups them differently. Here it takes the first 2 points, makes a line. Then it takes the second of those and the next point and makes a line. The second of those and the next one makes a line, and so on until it gets to the last point. One more variation is called line loop, which is exactly the same, except that it also puts in a segment from the last vertex back to the 0th vertex. Okay, triangles we've seen, and just as sort of a thought experiment, let's think for a minute about what we're going to see if I just tell it to draw triangles using this set of vertices in the order that I've shown. So we know from what we saw before, it's going to do something like, and let me draw it. Yeah, okay, so let's, before I reveal the answer, but yeah, both of you are right. Right, we know it's going to take this one, sorry, I want this. It's going to take this one, and this one, and this one, and make that into a triangle, right? And of course, it'll be filled in. And then remember what it did in our first example. It forgot about those three, and it went to the next three and said, this one, and that one make a triangle. And then it tries to go to the next three and make a triangle, but there aren't three. So it stops right there. And if we check it out, there it is. Okay, so that's what triangles do. It just takes groups, independent groups of three. So what's occasionally useful is what's called a triangle strip. And let me keep you in suspense here just a little bit. What does a triangle strip do? We're gonna make a triangle out of the first three, but then instead of just going to the next 3 points, it goes to the second point and makes a group of three out of that one and the next two. Then it goes to the next point and makes a group of three out of the next two. It goes to the next point, makes a group of three out of the next two. And next point makes a group of three out of the next two, makes a group of three out of the next two, and then it's run out because it would. This is the last point right there. So we should see something like that. Yeah, so that's a good comment. You know, the triangle strip seems more useful. And yeah and no. I mean, the argument for using a triangle, something like a triangle strip, is that it can be a little bit more efficient in terms of the use of data. The problem is it's a lot more confusing to set up a model in terms of triangle strips, because what you have to do is take a model that is made of triangles and figure out, well, how do I group these into a strip so they can share more vertices? So it's not as commonly used as you might think, in my experience. But anyway, there's triangle strip as predicted. Does it impact performance that we have some apparent redundancy drawing over pieces? And the answer is sure, it does. Yeah, because we're drawing some pixels multiple times that maybe we don't have to do. And finally, yeah, let's do one more. So the last one that's an option for us is called triangle fan, and this is sort of a different thing. So we start out picking 3 vertices to make a triangle. And then what it does is it retains the first one and uses that one and the next 2 to make a triangle. And it retains the first one, uses that one and the next 2 to make a triangle. Uses that one and the next 2 to make a triangle. That one and the next 2. That one and the next 2. And so we would get something like that. And if we go to look at that, there you are. So that's perhaps an efficient way to fill in an entire blob or an entire polygon or quad. But again, the real restriction that you're faced with in doing this is that when you get a model, it's probably not you who has created the model, right? And when you get the data for the model, it's going to be organized in a certain way, and 99% of the time, it's going to be triangles. Because that is what Blender is going to give you, basically. Yeah, so anyway, that's kind of just a quick overview so you can be familiar with those possibilities, because occasionally they're going to come up. All right. Are there questions about, let's go back to this picture. Are there questions about this process that you want to, say, bring up at the moment? Okay, I think times at 9:30. Okay, we're doing fine. Let me show you indexing, because that seems as kind of like it's kind of relevant at this point. Now, if you where is it? Yeah, if you look at our vertex data, one of the things that might bug you a little bit is that there's some redundancy here, right? I have listed 6 vertices in the order that I want them grouped into triangles, and that seems very natural and simple, and we like it for that reason. On the other hand, you know that I really only have 4 points to talk about, because I'm making a square and it has 4 corners, and you can see that for example the vertex half half is duplicated, and the vertex minus half is also duplicated because it appears in 2 different triangles. And it seems like there ought to be a more efficient way to do this. So couldn't we just have an array of vertex data in which each vertex appears once, and then index into it? And that's what the idea of indexing is. And we will use this and see it occasionally, particularly when you want to, for example, draw a wireframe. The way you would do it is you would set up a different set of indices into the same vertices that was appropriate for drawing lines between each pair. So I have an example here somewhere. Oh, it's way up here. Okay. All right, so here, what we could do is we could just list our 4 vertices really in any order whatsoever. And then we would take an array of indices that say we want to go from minus half to half minus half up to half half. So 0, 1, 2 in our array, and that's our first triangle. And then we want to go from minus half up to half half, and then back to minus half half. In other words, indices 0, 2, and 3 in our array. And that would be another way of describing those 2 triangles. In this case, it actually isn't any more efficient because we have so few vertices. But again, if you're dealing with a model that's got thousands of vertices, and each vertex appears in 4 or 5 different polygons, then this can be a lot more compact in terms of raw memory. So I thought we should look at how this works. And I think it also helps, this example will help sort of reinforce this point about how data is used. So how does it look if we want to render this way? There's some very slight changes. So back here in our initialization in main, whoops, where did I just go? I now have to create 2 buffers. So I'm going to take the vertex data and load that into a buffer, and I'm going to take the index data and load that into a buffer. And another thing to notice that I didn't mention when we were looking at this is notice that in the vertices, remember, we take a JavaScript array, which is just this data in the square brackets. So this is just how you define a JavaScript array literal. It's same as Python. But we can't pass that data to the GPU because it's not really an array. Even though JavaScript calls it that, it's really an object. It's a mapping from basically strings to values, where the strings are representations of numbers, so we can think of them as indices. It's really sort of silly, but that's what they do. So what we have is we have this constructor, float32 array, that actually converts our JavaScript array into a real contiguous chunk of memory with floating point values in it. And we have to do the same thing with the index array. We start with a JavaScript array of these integer values, and from that we construct a typed array of type uint16. So these are basically unsigned shorts. Anyway, so that's, again, every time I come back to teaching this course, I never remember that. I have to look up what type of array I'm supposed to use for the indices. Is it int16 or is it unsigned int? Is the I capitalized or not in the type uint16? So just look it up in the example and you'll be fine. So anyway, let's take a look also at this function create and load index buffer, because there's one little difference to think about, and this is back in util, which is here. And if I look in the outline, some things are the same. GL create buffer. In other words, we want to allocate memory on the GPU. We need a handle to talk about it. And notice that when we call bind buffer, we're using a different binding point. Instead of using array buffer, we're using element array buffer. And that's the binding point that is used for indices, as opposed to a binding point for vertex data. And that's the only difference, really. The call to buffer data looks exactly the same. This is where we actually pass our raw data in, and it's associated with whatever buffer is currently bound to that register, just like we saw with the other form. So if you look at these two functions, create and load buffer with some data, or create and load index buffer with some data, this is the only difference, is the binding point. All right. Then the other difference here you'll see is that when you go to draw, well, actually there's two differences. I guess I better show you. Yeah, the two differences are you have to, this part's the same. We bind the buffer with the vertex data, we enable it, we set the pointer according to the attribute index, and then we can forget about it. But then the second piece is that to do the draw call, we have to bind the index buffer, again, to that element array buffer binding point that's used for indexing. And when we do a draw, we don't say draw arrays, we say draw elements, which tells it to use the element array buffer as indices rather than take the data directly out of the array buffer, the way we put it in. So this is how we do it. And once again, you have to specify the type of the index data, unsigned short. You have to specify the starting point in the buffer, that's the 0. And you have to specify not how many vertices to draw, but how many indices to use. Now, why did I not use a literal here? It would have been so much simpler. But num indices is 6. I wanted to draw 6 of these things. We can just put a 6 there. So then when we go to render this, hypothetically, if we go to render this, if I can find it, it should look exactly the same. And if we go back to the source code and I say, well, only take 3 indices, what would happen? And you guessed it, it'll only draw the first triangle, right? So that's how indexing works. And that's an option. We don't use it a ton. I mainly like to introduce it for the purpose of being able to draw wireframes. because for a wireframe, you actually want the vertices in a different order. And you mentioned using many similar rendering modes leads to the rendering runtime to turn more into a constant, having many different rendering out of O1. John, I don't think I understand that question. I don't think I remember having said anything like that similar rendering modes leads to the rendering runtime to turn more into a constant. Maybe you're mixing up where I was talking about uniform variables, right? That if you can use one global variable to represent an unchanging value, that's always going to be more efficient than having to take a varying value that is passed separately into each run of the vertex shader. And that's really no different than it is in ordinary programming, right? Having a global constant is going to be a faster access than having to look up a value a cajillion different times. But I mean, none of this is ever constant time, right? It's always, you're always going to be rendering multiple objects with multiple vertices into multiple fragments. Yeah, other questions about that example? Okay, I think we do good here. Yeah, the next thing to think about is we've talked a very, very tiny bit about the roles of the shaders. And I think I mentioned last time, where's my, that the fundamental job of the vertex shader is whatever else it does, and it could do a lot of stuff, but whatever else it does, it has to set the built-in variable GL underscore position. The fundamental job of the fragment shader is to set built-in variable GL frag color. And if you forget to do either of those things, nothing will work. Now, each of those shaders can have arbitrary code in it, so it could do a lot of other stuff, and we'll do much more stuff later. But fundamentally, these are the basic things that absolutely must be done, or else nothing will happen. Okay, so let's think about this a little. And one of the things I want to introduce is the shader editor, which is an add-on to Chrome. And before I do that, I suppose I need to, yeah, I need to show you the animation loop. Let's look at that. So going back to example 1A, notice in the first code example we did, we just issued one call to our draw function that does that series of per frame steps. And so it essentially rendered a static image that is unchanging. Much more typically, we will want to be able to modify some state and then draw again every frame. And this is how we'll be able to do animations or make the thing reactive to user input, so you can do games and stuff and so on. It has another useful side effect doing an animation loop, which is that we can dynamically make modifications to the shader using this very clever Chrome shader editor and see the effects in real time. And I want to show you how that works. The animation loop, the way this is typically done, well, you have a built-in JavaScript function called request animation frame. And the argument to request animation frame is a callback function. And basically what this says is, as soon as you are done rendering the previous frame, run this function on the next one, right? And it's a way of getting things to basically run as fast as they can, as fast as the browser can refresh them. There are other tricks to get things to run at a certain time scale, but we're not going to worry about that too much. So yeah, we take a function called animate, we pass it into a request animation frame. And what do we do in the animate function is we draw. And notice what's happening here is I'm defining this function, right? Remember, in JavaScript, functions are first-class objects, so you can have variables that refer to functions. So I'm defining a variable animate, which is our function. And within that function, after I draw, I'm going to call request animation frame and pass in a reference to the same function. So this is effectively our animation loop. It looks a little bit like recursion, but it isn't. It's a loop of a particularly bizarre form. And so this piece of code defines that animate function that will continually pass in itself as the next thing to do after the previous frame. And then we have to call it once to get the whole process started. So that's how the animation loop works. And don't worry about this too much because it's boilerplate, right? We're never really going to modify this other than to put more stuff inside this function. All right, so when we run this, notice it doesn't look any different. And let's bring it up. This is GL example 1. Oh, let me, well, it doesn't matter. This is good enough. We don't need the whole square for what I want to show you. And let me move the chat to the other side. I know you can't see these little windows probably, but they're interfering with my view of the browser. All right, so if you install this shader editor add-on to Chrome, then when you bring up your developer tools, you'll have an option up here for the shader editor. It'll ask you to reload the program, and if there aren't errors, it will load again, and then it will list the shaders on the side. We only have one shader program, namely, the one that we use to render this red polygon. And if I click on that, it will bring up the source code for the two shaders. So far, so good. I mean, we already knew what the source code looked at because we had it in our HTML. The interesting thing about this is that this is the source that is being stored on the GPU, and it's making a request to the GPU to show it to us. And the nice thing about doing that is that we can now monkey around with it. So what do we have over here? We have a vec4 representing the color red. So red 1, green 0, blue 0, alpha 1, being assigned to the color for each fragment. Well, one easy thing to see is, well, what if I change it to red 1 and green 1, I get yellow. And the nice thing about having that animation loop in place is that you can see the effects immediately. So this is one of the most useful tools you're going to have in getting through this course, is being able to dynamically experiment with what the shader is doing, because you don't have a debugger. And this is the thing that will drive us nuts in trying to get graphics programs to work, is that because you don't have a live debugger on the GPU, you're going to end up doing two different things. One is you are going to learn quickly that you have to be super, super careful in using a slow incremental development process to develop graphics code. In other words, you have to start with something that works, and you have to make tiny little changes and test them at every step to make sure you didn't screw it up. Because if you make 10 changes in a working program and it doesn't work, it's very hard to figure out where you messed up. And it's very easy to mess up, I can tell you. So this is one of my favorite tools, is the shader editor. Just for shits and giggles, let's try a few more things that you might be able to do, for example, in the fragment shader. So one of the things is, I'm just showing that you can edit. What else might we do? Well, a useful function in the shading language is something called discard. For example, you might discover in processing a fragment that, I don't actually want to render anything at this fragment position at all. how might you do that? Well, let's just do something sort of silly. We can put a conditional in here. We can say if, and let me say mod. I'm getting lots of error messages from the compiler. If mod, and I'm going to take GL frag coord dot x. I'm going to mod it by 20. And this is something that is continually annoying. No matching overloaded function found. Now, what's the problem? The problem is it will never mix integer and floating point values in GLSL programs. So I can't mod by 20. I have to mod by 20.0 because fragcoord.x is a floating point value. Now, as you might gather, this is another built-in variable. And the fragcoord.x and the fragcoord.y represent the fragment coordinate within the canvas, within the frame buffer. So my frame buffer is 400 by 400. And so what I'm saying is if I mod by 20, and if I discover that that value is less than 10.0, then what I'm going to do is I'm going to discard the fragment. Otherwise, I will render it in, let's say, red. Right? So that's an example of using this discard keyword in GLSL. And it shows that, yeah, you can do some sort of programming-like things within the GLSL, right? So you can see here it does have conditional statements. It has a mod function. So basically, I'm making stripes that are 10 fragments wide, 10 pixels wide. So this is probably not a real useful thing to do. I'm just trying to illustrate some of the things we can do in the fragment shader. Another thing we might do is we could take, well, let's do this. Let me take glfragcoord.x and do something like float c gets the value glfragcoord.x divided by, say, 400.0, of course. And I can't do that yet. See where it says no precision specified? Yeah, this is just something you have to get used to. If you want to declare any variable within the shader, you have to specify, well, I should say, if you want a floating point variable within the shader, you have to specify precision. So we type precision medium p float, which says when I say float, I mean a medium precision float. And that should be adequate for most of the things we do. I don't have an if, so the else is a syntax error. And what I want to do is instead of turning up the red to 1, let me turn up the red to C. And you can kind of see what happens is I've got a value fragcoord x that varies from basically minus 100 to plus 100. And if I divide it by 400, which is the whole range of my canvas, I will sort of get a value between 0 and 1. I guess in this case, it's only going from minus a half to a half. And I'm using that as the red. So I can get this gradient across based on the x coordinate. Tim, what are you talking about? The equivalent of a print statement? All right, maybe we'll come back to that. Other question, can you make a simple animation kind of thing by incrementally modifying a variable? Absolutely. We are going to do that pretty much from Thursday on out, assuming we don't quite get to it today. And that'll be a fun thing to do. I'm just trying to get across the idea that you can do creative things in the fragment shader. Yes, exactly. Yes, thank you, Tim. Yeah, the idea of kind of incrementally making a change and seeing what it renders is a lot like using a print statement to do debugging, because you don't really have a debugger. You have to just sort of produce some recognizable output. So very often when I'm trying to debug something and it's not looking right, I'll draw it as a wireframe instead, or I'll change the color to something constant and obvious, like instead of drawing this the way I wanted it, I'm just going to draw it solid red and see if it stands out enough for me to recognize where it's going wrong. So anyway, this is just some simple examples, and we'll play around with the fragment shader quite a bit more later. But I guess it's fair to say that in the near future, we are going to be much more concerned with the vertex shader, because this is where we are dealing with transformations. And that's the place to start. It's when we start getting into doing things like texturing and lighting and shading that we will spend most of our attention on the fragment shader. And that's where the sort of the really creative and clever things that you do with special effects is going to happen. All right, let's turn our attention to the vertex shader for a sec. And rather than doing it in the shader editor, well, you would do the timing in JavaScript, not on the GPU. And so yeah, you have timing available in the JavaScript code. You can control the frame rate and so on. Let's look back at our friend GL example 1A, and I'm going to go into the JavaScript where we have our original position. And what are the kinds of things we do in the vertex shader? And I remember I tried to do sort of a preview last time. So here at the top of my browser window, I wanted to sort of give you kind of a teaser of what the vertex shader is for. And this is really what it's for, is to do these things, right? We have to be able to take a model, place it into a scene, a so-called world. We need to be able to take that world and transform it into camera coordinates, so we get a rendering of it from a certain viewpoint that we specify. And then we have to specify the field of view and transform that into so-called clip space, this predefined 2 by 2 by 2 by 2 by 2 cube that represents what is actually going to be fed into the next two stages of the pipeline. And we're kind of bypassing the model and the view and the projection transformations now by just drawing using coordinates that are in that 2 by 2 by 2 cube. And so they are successfully being fed into the rest of the pipeline. If we pick a vertex, let's do that actually. So where are we? I guess what I want to do is reload this. What if I take our code? Not that. I want to take our code, and instead of let's just try this. This will be fun. Instead of a vertex at half a half, what if I put a vertex at 3.0 a half? Right, now that is outside clip space. So not surprisingly, it's going to, am I loading the wrong code? This is 1A. 1A. Did I forget to save it? No. Oh, I'm drawing the wrong triangle. That's fine. That's why we can't see it. Here. That point isn't in the second triangle. There. So what's happening here is all the math is working great. It's rendering the triangle the way we specified it. It's just that it has to get clipped off because it's outside the clip space. That's how that works. Simple enough. I mean, the algorithm that does this is actually a lot more complicated than it looks. Because remember, it can only draw triangles. What have we got drawn? We have a quadrilateral. So internally, it has to basically make new triangles to simulate the fact that having done this clipping, it is now a different form of polygon. So the clipping algorithm is not as trivial as simply eliminating everything that's outside of that cube. It actually has to do some work to make it possible. But we are not going to get involved in the clipping algorithm. I think this has become, when I first taught graphics back in 1993, this was one of the things we had to spend a lot of time on was how do you do line drawing? How do you do clipping? And there's some well-known algorithms that have been around since the 70s for doing these things efficiently. But I don't think we really need to get into that anymore because it's all hard-coded in the graphics card now. So what do we really have to learn about it? I mean, we're never actually going to write code that does those things because it's hard-coded in the graphics card. So it doesn't seem like a good use of our time to study clipping algorithms and so on. But you can find it in any graphics textbook if you want to look. Where was I going with this? There was a point. Oh yeah, I wanted to just experiment with shader code. So let's put this back the way it was. There's my data. And let's imagine we wanted to do something like, where's this? Instead of drawing it the way that the vertex data comes from the buffer, what if we wanted to shift it over to the right by 0.2 of a unit? How could we do that? And it's not too hard. I would maybe do it like this. We take GL position dot x, and I want that to be a underscore position dot x plus 0.2. Well, first let's see what that does. And it should be our same little triangle, but shifted 0.2 of a unit to the right. So this is kind of cool, and it actually illustrates a number of things about the GLSL language, which is when you have one of these vec-type variables, vec2, vec3, or vec4, you can access the individual elements in a number of different ways. Most convenient that I used in both examples, the frag chord example and this GL position example, is .x, .y, and .z. And this is one way we could do it, is just set GL position and then alter the x component, which is the first component of that tuple, by shifting it to the right. Right, so this is a really nice little syntactic thing they built into the language. The language is streamlined for doing convenient things with vectors and matrices, and this is one of them. This is also very cool. You could do GL position XY gets GL position, I guess I could do it this way, vec2 position plus 0.2 position dot y. We could even do it this way, x, y, z, and then I don't even need this one. I guess I messed this up. This should be a vec4 now, and this can be commented out, and that should work too. W. That should do exactly the same thing. And so the four components can be named in this way. There are other alternatives depending on whether you're working with texture coordinates, in which case they're called S and T rather than X and Y, or if you're working with colors, you can call them R, G, B, and A. And one of the things that's sort of interesting is that you can swap them around. This is called swizzling by X. And now it switches the roles of X and Y. Pretty sweet too. So this is a convenient notation to be aware of, is that you can kind of individually access these things in kind of creative ways. But the other thing that this illustrates is that, yeah, one of the things we can do within the fragment shader is that we can shift around, we can transform vertex data. And this is something we're going to do continuously, pretty much from Thursday forward, is think about how do you transform the vertices to make the model do different stuff. And one thing to keep in the backs of our minds is what you generally don't want to do is you don't want to go back to the JavaScript and transform the data here and send it over to the GPU again. Running code on the CPU is moderately fast. Running code on the GPU, transferring data from the CPU to the GPU is really, really, really slow. So we like to avoid doing that any more than we have to. So the typical model is you take your vertex data, you send it to the GPU, put it in a buffer, and then you forget about it. You leave it there. And when you want to take the model and transform it somehow, you do that transformation in the vertex shader. Basically, using uniform variables in the form of matrices is how it's ultimately all going to happen. And we don't really know about how to do that yet, but I'm trying to illustrate that in that vertex shader, we do have the ability to perform transformation. Time to do this one more. Since somebody brought it up, I did want to kind of do this. Yeah, let's look at this. GL example 1A with animation. Oh, all right, well, let's do it. We'll have to come back and explain some things. So what am I doing here in our vertex shader now? I have a uniform variable that I'm calling the shift. And what we're going to do is set GL position to be the X position plus a shift value. This is another alternative for initializing GL position. Rather than actually specifying the remaining 4 coordinates, I'm just saying take the remaining 3 from A position, Y, Z, and W. And we're allowed to do this when we construct a vec fold. Again, there's lots of flexibility, but this will essentially do what we just did by shifting the X coordinate to the right or to the left, except that I'm going to use a uniform variable, which remember is like a global constant that we can set from the JavaScript. So 2 things to do. If we look in the JavaScript, in the draw function, where is it? I'm gonna pass in an argument, which will be how far do I want to shift for this particular draw call, and we're going to pass that value in as a uniform. And the mechanism for doing this, I'll have to review this next time because I'm going too fast, is once again, is done using kind of an index. You query the GPU for an index for that uniform variable, and then you use that index to set the value. But what I really wanted to look at was this: that in our animate function, we could start doing some clever things, right? So here I'm saying, well, my shift is going to be 0.2 of a unit, and so this will be the initial shift amount is 0.2 of a unit to the left, and I'll define an increment that I can change each frame. And what is this doing? Well, I'm going to draw with a shift value. If I go more than 2/10 of a unit to the left or the right, I'll switch directions. But otherwise, I'll just add the increment onto the shift value. So I'm going to constantly update that value when I draw. In the draw call, we'll set it as a uniform variable. And then the vertex shader will use that uniform variable to adjust the position of the model. And so let's take a look at what that looks like. You can imagine, I think, what it's going to do. If I can find it, animation. There we go. Right? So it's shifting 2/10 of a unit to the left and then gradually modifying that by some little incremental value. And when it gets 2/10 to the right, it switches the increment to be a negative number again, and it goes back to the left. And it does that pretty fast. Yeah, good question, John. It's just those specific types that we use. I am pretty sure it doesn't have arbitrary structs as a thing. So this is mesmerizing and will make you slightly crazy if you keep it going. So I'm going to stop at this point and turn it off. But I think that gives you a fair overview of the kinds of things that we're going to be able to do by monkeying around in the shaders. And I'll review how you work with uniform variables a bit more carefully next time, because I blasted past that a little too quickly. In between now and then, please do install the shader editor extension on Chrome and experiment with the things that we just did today, just to kind of get your head around a little bit of what's happening. We have another kind of debugging tool that's useful that I'll introduce next time. It's called Spectre.js, and you can install that extension too. I'll post a link when I post on the topics page. Meanwhile, any last questions before we part for the day? Cool beans. Well, thanks for coming, everybody, and hopefully I'll be back at headquarters with the whiteboard. Why do I look pale? Unnamed participant wants to know what I ate for breakfast, and the answer is strawberries and a banana and some granola. So there. Thursday's lecture will be posted just as soon as I can get 20 minutes free, because that's about how long it takes for me to upload it into Canvas. Yeah, right. Thank you very much. Yes, I am staying very safe. I'm a number of miles from the front at this point. I'll see you all hopefully on Thursday. So, Nick, send me an email and I will send you the link to my WebEx room and we can chat for a minute. Okay, how do I turn this thing off? WebEx meetings. Oh, I'm screen sharing. That's what I don't want to do. All right. Bye, everybody. I'll see you later.